So welcome back, everybody, to the second part of the session on fundamental principles. I'm Jason Green. I'm from UMass Boston. I'll be guiding us through this next session. There'll be 2 lightning talks, it looks like, and 2 invited talks. The first lightning talk's from Naruo Ohga, talking about Legendre duality and stochastic thermo. Go ahead.
Okay, thank you for introduction. Okay, my name is Naruo Ohga at the University of Tokyo. So let's consider relaxation processes of an autonomous detailed balance system. Relaxation is captured by several different quantities. So for example, the probability goes to an equilibrium distribution, or the thermodynamic force goes to 0. And the total entropy goes to its maximum in the equilibrium. Well, so among these quantities, one might say that P alone is sufficient to describe the relaxation process because it can be, any other quantities can be expressed as a function of P. But F is often more informative because it's directly related to these thermodynamic quantities. So here's a question. Can we fully and reasonably describe a relaxation process based on thermodynamic forces? Well, in this talk, I will answer yes by constructing this structure of Legendre duality. So it connects to a description of a relaxation trajectory. The left one is the conventional description, which uses P to describe the process. It's P to use P as a coordinate and use total entropy to describe the thermodynamic properties. So through the Legendre transform, we introduce a new description which uses thermodynamic forces to specify distribution and a new thermodynamic potential function to describe the relaxation trajectory. So this construction is inspired by a similar structure in information geometry. Okay, so let me explain the main lines of the construction and the result. The 2 descriptions just introduced are rooted on different view of relaxation trajectories. The left-hand side is rooted on the original dynamics, which is the free relaxation with no driving. Its thermodynamic property is given by the total entropy of the system plus bath. On the other hand, the right-hand side is rooted on what we call quasi-static dynamics. So it has the same trajectory as the original dynamics, but it is quite statically slow. It is realized by applying an external field and changing it to mimic the original dynamics. The corresponding thermodynamic potential is the equilibrium free energy under this external field V, and it quantifies the cumulative work of the driving. We write this potential as minus T psi of V, so which plays the role of thermodynamic potential in this new description. To state the precise form of the Legendre transform we construct, we need some more treatment. In the left description, we basically use P as the coordinate. However, we actually use instead a special coordinate system eta, which has linear and one-to-one relation with P. Similarly, in the right new description, we use a coordinate system theta, which is a linear and one-to-one relation with the external field V, and also in such a relation with the thermodynamic forces. So with all this setup, we obtain this Legendre transform as our first main result. In addition, we have another result. Both functions are monotonically increasing along the trajectories. So this property for the total entropy is just the second law of thermodynamics, but on the other hand, that force psi gives a new constraint on the time trajectory. So this states that in the quasi-static dynamics, we always need to inject positive work to mimic the original trajectory. So let's get into the detail. We consider n+1 discrete states with energies epsilon I. We consider single heat bath, and the equilibrium is the canonical distribution. The time evolution is the time-independent master equation. We introduce the total entropy by the sum of Shannon and energetic contributions. By rearranging the time derivative of the total entropy into this form, we obtain the thermodynamic forces conjugate to the transition from J to I. It vanishes at equilibrium and it is asymmetric. Okay, now I state the concrete construction of the quasi-static dynamics, which plays a key role in our result. We assume the external field V modifies the state energy from epsilon to epsilon minus V. We define V of P as a function of P so that it reproduces the distribution P as a canonical distribution. Since this equation leaves an ambiguity of adding a constant, we also impose this additional condition to define V of P uniquely. Then we define the quasi-static dynamics as driven by this V of P. We also have its relation to Fp. So V of P cancels out the thermodynamic force of Fp because P is the equilibrium under this external field. So we have this relation. Okay, next I explain the construction of eta and theta coordinates. So the set of probabilities P, we use this as basically as a coordinate, but the set of probabilities B has n+1 component. And with this linear constraint, we have only n independent components. So we arbitrarily choose n independent components and use it as eta coordinates. We do something very similar also for V. So V has n+1 components, but it has one constraint. So I reduce it to n component theta coordinates. And finally, here's the explicit formula of the two functions, the total entropy and the equilibrium free energy under this modification by the external field. So with this construction, we can finally state the result formally with this Legendre transform of between these coordinates and these functions. Okay. So, well, we have another result. It states that this set of coordinates and functions can be interpreted as a dual affine coordinates in information geometry. So I do not have time to explain what it really means, but as one of its consequences, the two functions have an information geometric expression using the KL divergence between P and P equilibrium. As a result, the functions are both monotonically increasing along the relaxation trajectory, which gives the second law of thermodynamics and a new constraint on relaxation processes. Okay, so in the end, I will demonstrate our two results by using a concrete three-state system. So let's consider a three-state system with one unstable state and two stable states. The relaxation rates are biased. And we choose an initial distribution that concentrates on the unstable state. So it first relaxes to this state, and then it goes to an equilibrium. We choose the coordinates to reflect the symmetry of the setting. So concretely, the eta1 and theta1 are non-zero when the probability between 1 and 2 are imbalanced. And eta2 and theta2 are positive when they have excess probability at state 0. So with these coordinates, with these eta coordinates, the trajectory looks like this. It's a two-step relaxation. This is not surprising because of the biased relaxation rate. On the other hand, in the theta coordinates, the process looks like 3 stages. So the imbalance theta1 first grows, then it stays constant, and then it decreases. So this model shows that we can capture a new separation of a stage, or more generally, we can capture new insight into the trajectory using theta coordinates. So, and moreover, in this model, I don't have time to explain, but the emergence of this new stage can be explained using this new constraint. Okay, so this is the summary. And before concluding, let me emphasize 2 points in our construction. First, we can use, with our construction, we can use a set of thermodynamic forces as a coordinate system. So this is what we wanted to construct in the introduction. And in fact, it gives a new insight into the process, as demonstrated by the model calculation. Second, the newly introduced potential at equilibrium free energy. So upon analyzing relaxation process, we may be able to start from its equilibrium properties. So we calculate the equilibrium free energy and the external field, and then we perform the Legendre transform to get information about the non-equilibrium dissipation. So in this way, it may give a new connection between non-equilibrium and equilibrium properties of a system. Okay, for more details, please see our preprints and its chemical thermodynamic counterpart also. Thank you for listening.